Here we have a Bowditch curve or a Lysagous figure. And they can vary from this. This is just an example of one. What we're going to do with this graph, these two parametric equations, we're going to find the point in the interior of our first quadrant, so somewhere in here, where the tangent to the curve is horizontal, and you can see that's going to happen at a max or a min. So roughly right there. We have to figure out what that x value is, or what that ordered pair is. And then we're also going to want to find the equation of the two tangents at the origin. Okay, so we want the equation of these two lines. So if we remember from Calc 1, we're going to find the point where the tangent's horizontal. That's where the derivative is equal to 0. So we're going to need to determine the parametric derivative. And to start by doing that, I'm going to take the derivative of x with respect to t, dx dt, and that gives me 2 cosine of 2t. I'll also take the derivative of y with respect to t, which is 3 cosine of 3t. And in this situation, we want to solve where the derivative is equal to 0, so we need dy dx. And dy dx, that derivative, is formed by putting dy dt over dx dt. So ultimately, to determine the point where the tangent line is horizontal, we're going to need to solve that derivative equal to 0. And this is a pretty complex problem to solve the way it is, so we're going to go through some manipulation using algebra and trig and some identities. So in the numerator, I can use a sum and difference identity. So if I say that 3t is equal to 2t plus 1t, then my cosine sum identity would give me, I've got cosine 2t times cosine t minus sine of 2t times sine of t. And in the denominator, if I use a double angle, the 2 would remain, and my double angle for cosine is 2 cosine squared t minus 1. And essentially what I'm doing is getting this into some sort of factorable form so that it's easier for me to solve. And just to clarify what was done there, I used a sum difference, 2t plus 1t, to use my cosine sum difference, and then down here I used a cosine double angle. So I'm reducing these, my double and triple angle, I'm trying to reduce them down to 1t because that will make it easier for me to solve. So I still have 2 cosine and sine. I've got 2 double angles in my numerator. So I'm going to sub a double angle in again for each of those. So I've got 3 times cosine 2t is 2 cosine squared t minus 1. And then we still have the times cosine t minus sine of 2t, which we can rewrite as 2 sine of t cosine t, and we'll still have to multiply that by sine t, all of which is over 2 times 2 cosine squared t minus 1. So this was my cosine double angle, and then the 2 sine t cosine t was my sine double angle. So I'm reducing those variables in the argument of my trig functions down to a single variable. At this point, we've got some substitutions that we can do. I'm going to clean it up a little bit first. So my next step here, I notice that both of my 2 terms in the numerator have a cosine t. So I'm going to factor that out. And notice that 3 was still in front of all of that expression in the numerator. So I have 3 cosine t, that leaves me with 2 cosine squared t minus 1 minus 2 sine squared t, all of which is over 2 times 2 cosine squared t minus 1. So I see this is starting to simplify a little bit here. I do know an identity, and since I see that I have all cosines and just this one sine, I might use a Pythagorean identity. So remember, sine squared t will be equal to 1 minus cosine squared t. So here I have 3 cosine t times 2 cosine squared t minus 1 minus 2, and sine squared is 1 minus cosine squared t. All of this will be over 2 times 2 cosine squared t minus 1. So distributing that 2 to both the 1 and the cosine squared, I can collect some of the terms in this set of parentheses, clean that up a little bit. I have 3 cosine t times the quantity 4 cosine squared t minus 3, all over 2 times 2 cosine squared t minus 1. So now I have everything in terms of cosine, and I have everything factored. This represents my derivative, dy dx. So now that we have our derivative, we need to determine where the tangent line is horizontal, and that means the slope of the tangent line needs to be 0. The derivative tells us the slope of the tangent line. Therefore, we're going to need to solve this derivative equal to 0. So solving this equal to 0, my derivative here, notice that 0 is over an invisible 1. So cross multiplying, we would get the numerator equal, and if I multiply these guys, I end up with 0. So I have 3 cosine of t minus 4 cosine squared of t minus 3 is equal to 0. So in order for me to solve that, I would solve each of these pieces. I've got 3 cosine t equal to 0, or 4 cosine squared t minus 3 equals 0. So my first equation on the left, that would be the same as cosine t is equal to 0. And where would t, as an argument of cosine, provide us with an output of 0? And that would be at pi over 2, or 90 degrees, and then 270, 3 pi over 2. All right, but we're only concerned with quadrant 1, so we're going to leave out that 3 pi over 2. And for the other one, if I add 3 and divide by 4, I've got cosine squared t equals 3/4. And square rooting both sides, that is cosine t equals plus or minus root 3 over 2. So we've got plus or minus the square root of 3 over 2. And where does t equal that if that's my output? We've got pi over 6, 5 pi over 6, 7 pi over 6, and 11 pi over 6. Okay, but again, we're only dealing in quadrant 1, so we don't have to worry about those other values. So essentially we have 2 t values in quadrant 1. And since t equals pi over 2 is on that y-axis, we're not going to use that. So we're really just concerned with t equals pi over 6. So the tangent line is horizontal at t equals pi over 6. And just to expand on this part of the problem a little bit, we could write the equation of the tangent line here. Of course, we know that the slope is 0. So the slope being 0, that means the equation of that line is going to be y equals a value. So we just need to know what y is equal to at pi over 6. if you recall, my y equation was equal to sine of 3t. Y equals sine of 3t. Well, if I take my t and I plug in pi over 6, that's sine of 3 pi over 6, or sine of pi over 2, and sine of pi over 2 is 1. So we would get y equals 1. That would be the equation of my horizontal tangent line at t equals pi over 6. So let me clear this screen and we'll go back up and do part B. So we're going to find the equation of the two tangents that are occurring at the origin, which we know the ordered pair at the origin. The ordered pair at the origin is 0, 0. But we need the slope. And so we need to know when, or at what value of t is x equal to 0 and y equal to 0. So I've written that question here. What value or values of t allow x and y to equal 0 simultaneously? So we need to figure out what numbers to plug into our equation for t that are going to give me a 0. And with a little bit of thought, we can determine that that's at t equals 0 and at t equals pi. So in this case, we would need to evaluate our derivative dy dx for t equals 0. That would give us a slope at t equals 0. So I've got 3 times the cosine of 3 times 0 over 2 times the cosine of 2 times 0. And that simplifies to 3 halves. So that is my slope. So in this situation, if I were to write that equation, remember my ordered pair is 0, 0. I would say y minus 0 equals 3 halves x minus 0. We would get y equals 3 halves x. So that is the tangent line at t equals 0. And we could also evaluate the derivative for t equals pi. 3 cosine of 3 times pi over 2 cosine of 2 pi. And cosine of 3 pi is equal to -1. So we end up with -3 halves for my m value. All right, so the same situation here, we would use that point in our point slope equation, but with -3 halves. And we would solve and determine that the equation of the tangent line at the origin would be also -3 halves x. So that is when t is equal to pi.